Hi everybody and welcome back. We're going to take the first steps here on our mission to more accurately predict hurricanes using the core engineering design process. This means we need to define the problem and start doing some research. This is probably going to bleed into the next episode a bit as well, and maybe even a couple episodes after, since in my experience the process in general involves a lot of iteration. Also, I was planning to show my preliminary brainstorming session here, which I generally do before I do any research whatsoever into existing solutions so I don't bias my thinking. But as I started cutting this episode together, I realized, this is getting pretty long. It makes more sense to lump that into the next episode so I can just cover the general process of brainstorming once. Plus, there's a lot of basic research to cover. I'll try to clearly differentiate between my preliminary brainstorming session and what I added later on, in the next episode, so it's all pretty clear. Anyway, let's just get started. The first thing we need to do is come up with an initial problem definition. A mistake in formulating this correctly will torpedo the project before it even starts, so we need to make sure that we do this right, as everything else we do will be derived from it, including our design requirements and metrics for success. A proper problem definition should convey what we're trying to accomplish with a clearly stated, verifiable objective. So we wouldn't say, for instance, current hurricane forecasting systems need to be improved. Improved how? Improved by who? Improved so meteorologists spend less time with a model? I mean, if that's our goal, then we could just create a system that always says this hurricane is going to be hitting Timbuktu in 24 hours. And that would be better than the old system because meteorologists won't have to spend all that time forecasting. But for literally everyone else in the world, that system would be useless. And in the end, it probably would be bad for meteorologists too, since people would just give up entirely listening to them and they'd be out of a job. Also, the problem statement shouldn't be so specific that it forces you down a specific design path, unless you've got some clear requirement from the client. So we wouldn't want to say something like, we need to increase the forecasting accuracy of physics-based algorithms in use today to such and such a threshold, because that would commit us to using a physics-based algorithmic approach here. And we couldn't really, start using machine learning. We couldn't pull in alternative data sources. We'd be very limited in what we could actually do. No, to create a solid problem statement, we first need to consider who we're solving this for, why it's important to solve, and then determine some specific measurable objectives that would mean success if met. We also need to make sure we don't force ourselves down a specific design path unnecessarily. Now in this case, since I don't have a client who's hired me to help them with some specific task, I want to think first about who do I want to help here? Who would benefit the most, or perhaps what's the largest affected group that I could help by improving our hurricane forecasting ability? If I were trying to do this for some sort of financial gain, I might think about where is the greatest business opportunity? What groups would be willing to spend money for this? And how could I build a system to attract them? But ultimately, what this really just boils down to is first answering the question, who will use this system? I can then do some research and determine what about the existing system's performance needs to be improved in order for my particular user's experience to benefit the most. And then eventually, in the concept generation phase, which we'll get into in the next episode, I'll think about how do I go about doing that. Now again, if you have a client or are given a problem to solve in some other way, this is all a lot more clear-cut. But I like this example here because it really makes us dive into the full process, which is what somebody trying to invent something new to build a future business around would have to do. Now, I start off by categorizing potential users. You can just use a pad of paper to do this, but mostly for demonstration purposes here, and because my handwriting is atrocious, I'm going to use a tool called FreeMind to create what's called a mind map. There are a number of tools out there that you can use instead. I'm just picking this one because it's free and it works, well enough. We'll also use this tool in the concept generation step, but we'll follow a stricter set of procedures when we get there. So here, I've already done this mind map, but I didn't want to make you all suffer through watching me type it all out since this is already going to be a pretty long episode. So I'm just going to quickly go through what this is and how it works. I start out by labeling the central node, which, I mean, you don't really have to do that, but just for the sake of doing this correctly, I'm thinking of different types of users here. So I have 6 potential groups that just come to mind offhand, like high-level groups. First are people who are at physical risk, those that are at financial risk, utility companies, meteorologists, corporations, and government officials. There are likely others that I'm not thinking of, but nobody's perfect, and really what this exercise is intended to do is just sort of spark thoughts as you go, and as I think of each of these groups, I can next think about people that fit within each. So looking at the first group here, people who are at physical risk. When I think of that, I'm thinking about people who may be injured as a result of this storm. Where were they? Were they at home, on the road, or at work? What were they doing? Do they have a dangerous profession that became more dangerous because of the storm, such as first responders or fishermen, or maybe they're working in transportation, hauling freight on the road, driving a truck, or maybe they're at sea. There are a bunch of professions that may be affected by a storm like this. Were they trying to evacuate, but they were unable to? If they were unable to, why was it? I mean, offhand, I can think of disabled and elderly people not being able to, but maybe they didn't want to, and I think this is probably better in this category here. Maybe they're unable to because they simply didn't have a car or enough money to pay for a ticket out of town. Maybe they didn't want to because they didn't want to leave pets behind or didn't believe the forecast. So people at financial risk, there are a few categories I can think of here. People who would suffer property damage being the most obvious. Homeowners, people who own cars that are destroyed in flooding and whatnot, small business owners. But then there are a whole group of other people who are affected as well, people who lose income because of the storm. So hourly workers, if the stores are closed, they're not going to be able to go. Hourly and full-time employees at small businesses that were destroyed. So it's not just the owner of the company that is affected here, it's also the employees. Taxpayers, obviously, if FEMA comes in to clean up, there's going to be a bill associated with that the taxpayers are all going to have to pay. Local initiatives may end up having a larger impact on that. And then if there are a number of insurance claims in an area, then the ratepayers are going to be fronting that bill. You're going to see our rates go up. So when I think of insurance ratepayers, I should note here that I'm really thinking of the insurance companies as being a potential user. So I don't have that explicitly named here, but the point of this exercise is to make you think of groups that would be good potential users for this system. Utility companies also, they're controlling the infrastructure, so with utility lines being above ground, I could see a lot of issues related to that. Obviously, down power line is going to block traffic, which could be a problem for people trying to seek medical treatment. But let's say the power to the hospital is taken down because of the storm, then that's going to be a problem for everybody, not just those that live in a particular area. So within the group of meteorologists, who's probably the first group that we all think of when we think of potential users here, there are actually a couple different categories that apply. Not all meteorologists, for instance, work for television or radio. A number work at consulting companies. I used to work at a company for a meteorologist named Dr. Donna Blake, and she was one of my first mentors. We worked together on a project when we were consultants at this company to the Navy, and it was a very cool project. We had to model the weather in a pretty high level of detail so that we can simulate the performance of different sensors. I don't want to get too much into the details there, but she went to school for this and knew far more than I ever will about how the weather works. So my role was basically taking the knowledge that she had and then translating it into code. So that was a pretty fun job. I really had a good time doing that. And you know, it's a viable potential route to go. Maybe if this thing works well enough, sell it as a service for a consulting firm that maybe I create. But you know, I think that's probably not the way that I'll end up going here. Also, the government, NOAA and the National Hurricane Center, I believe that's actually within NOAA, but you know, for all intents and purposes here, you can see them as two separate entities and potential users of the system. Corporations, Google, Amazon, etc. I mean, they all have their own algorithms to predict the weather. And if you're using, say, an Echo Show device from Amazon, it'll show you the current forecast on the screen. If you ask a Google Home device what the weather is today, it will tell you what it is. So I don't know if they have specifically hurricane forecasting systems built in, but you know, maybe that's a feature that they would be interested in procuring. Government officials at the state and local level, they're the ones who issue evacuation orders, so they would certainly be viable candidates to use this system. And at the federal level, we have the Army Corps of Engineers, FEMA, and again, the National Hurricane Center and NOAA as potential users. Okay. So which of these groups should we target, and what did they need from a system? To make an informed decision, we need to do some research. First, I went to NOAA's website and found a bunch of information about the costs associated with various storms. This page also lists some other facts, such as the top 5 most vulnerable states to hurricanes, which has to do with the property value of those states in areas most prone to flooding. This led me to NOAA's billion-dollar weather and climate disasters table of events page, where I found my first data set, which I quickly downloaded and plotted. This data set contains all the most destructive cyclones since 1980. The plot shows death tolls against costs. Dollars are consumer price index adjusted, though it's really not clear if this is just at a national level or a regional one. I'm guessing national level because they don't specify a baseline for a regional comparison. And pulling in a little US Census data, I was also able to do a similar adjustment to the death toll column here, you know, to get into more of a per capita rate. I say this is crude because you know, I looked at just the overall US population change year over year and didn't really account for regions because that would have involved a lot more work. But I'm really just trying to get something sensible I can work with here and just get a general idea of what's going on. I also scrubbed for outliers and plotted it here, and you can see there was a correlation with a 0.59 R squared, and tells me at least at a high level these are probably not independent variables. This can be attributed to a ton of different reasons, really. But you know, there's this exercise that we do in engineering, which is to think about a problem at its extremes, its boundary cases. So if I were to think about a hurricane hitting an area, and I were to say, okay, well, everybody in that area was evacuated beforehand, so it's just a bunch of empty buildings, there would be a lot of property damage and no casualties. So, you know, thinking about, you know, why there may be a correlation here, it may have to do with areas not being properly evacuated. And it's a speculation, there's probably more to it, but this does at least lead me in a direction that I can continue the research in. This led me to continue digging into casualties of these storms and see what information I could find. I found this LA Times article titled "Analysis. Most of Florence's victims have died in vehicles on the road during the storm." There's actually a lot of pretty interesting information in here beyond just the facts stated in the title. It talks about a 2016 study published in the Journal of the American Meteorological Society, which was written by officials from both NOAA and FEMA. In the 16 storms they studied from 1985 to 2008, 43% of the deaths came not from the storm itself or during when the storm hit, but before and after it had passed. Casualties of storms revolve around all sorts of accidents that just wouldn't normally happen, like being electrocuted while you're setting up a generator or poisoned by said generator, getting carbon monoxide poisoning, I should say. Also, after a storm passes, there may be damage to infrastructure that prevents people from getting to hospitals, or the hospitals may be closed. And that may be a reason why people die. They don't have access to the healthcare they need. Okay, along those lines, the article goes on to talk about this study that was published in the New England Journal of Medicine, which has been a hotly debated topic in the last few months. It suggested that as many as 8,498 people may have died because of Maria. And this was mostly, they say, attributed to the fact that they couldn't get proper medical treatment for things that might have normally been treatable. If you have a heart attack and you can't get to an ER, or there is no ER to go to, what may be a perfectly treatable condition turns fatal. Now, this reminds me of Hurricane Sandy. I live in New York City, and during that storm, there was a lot of damage, obviously, but the real travesty was what happened to hospitals and nursing homes near the water. They weren't evacuated until it was almost too late, and a lot of elderly people ended up being brought to some pretty hastily prepared shelters and living in some pretty bad conditions for a while. And then after the storm, people returned to communities where evacuation orders had been issued to find that a number of elderly people had died because they simply couldn't get out of their homes and couldn't evacuate. So it's really not just about issuing evacuation orders on time. It's about trying to get people out of those areas and also protecting them, protecting the infrastructure in the hospitals. If we really want to save lives, there's more to it than just simply issuing timely evacuation orders. So, getting back to our mind map, even if I wanted to focus on protecting property over protecting lives with this system, or vice versa, there's really only so much that a better warning system could do in the hands of private citizens. The areas that get flooded by storms are massive. No individual or even group of individual homeowners, let's say, would be able to build a large enough barrier to protect their homes, even if they had a full week to prepare, especially considering that everyone in the area would be, out trying to rent the needed equipment. And even if we had a better system in place to give the general public a better warning of an incoming storm, there's still going to be people left behind. And even if there aren't, people won't necessarily stay away long enough after the storm passes to be immune to some of these other effects. Local hospitals may be out of commission, roads may be closed, and if people come back too early and they say suffer a heart attack, that's not necessarily going to work out for them, and they may become a casualty of this storm. But if we create a system that garners better trust by the local, state, and federal governments, then perhaps they can mobilize their resources to protect both property and lives better. The Army Corps of Engineers can prepare an area or a hospital far better than a group of homeowners with some sandbags. And they can really ensure that the roads to those hospitals also remain passable, provided they're deployed in time. And a city government can organize shuttle services for disabled and elderly residents living at home. And if things look really bad, they can have more time to prepare shelters with medical personnel, food, and water for those who need to be evacuated, or deploy programs for stockpiling food and fuel, or work with utilities to shore up weak points in the power grid, or bring backup generators to vulnerable areas. But as deep as the pockets of government can be, crying wolf here is not something that even they can afford to do. All of these steps cost money, a lot of money. It's all about building a system that's more accurate than the one we have. Those sorts of stats won't necessarily win over the general public, but perhaps they can sell a government agency or a local mayor to listen to this system and take action the next time something big comes. They're the user, they're the ones that we really need to consider. Okay, so with our user finally identified, we need to go through other constraints that may come into play. This part's actually pretty simple. Time. There's only one person working on it, that's me, and I only have so much time that I can dedicate to it. I have other projects I'm working on at the time, and this is a hobby, so it's not really full time for me. Over the past few months, I've already spent a fair amount of time. Let's say 300 hours. I'm up to about step 5 and catching up with these videos, and I'd say I only really have maybe 200-300 more hours that I can afford to burn on this. It may sound like a lot, but say a small startup company or a team of people at a large company that are building something like, say, a 3D printer, they're going to spend thousands of hours, if not tens of thousands of hours, working on their design before they even ship the first unit. So a few hundred hours is really not that much. Money, again, this is just me. I have to keep this kind of on budget here. So I'm going to set this at a max budget 200. Obviously, this doesn't include my time, depreciation of the equipment I'm using, or any overhead expenses. But those are things that you may want to account for. I'll be sticking with open source, free data sets, and while I may need to procure some software or perhaps another hard drive, I think this should be fine. Okay, resources. I have 2 desktop computers. One with an i7-8700K, CPU, 980 Ti, GPU, 64 gigs of RAM, and some assortment of hard drives and SSDs. And another, it's a i7-2600K processor with 8 gigs of RAM and a 650 Ti GPU. And that has I think it's a 250 gig SSD. Expertise. My degrees are in mechanical, aerospace, and systems engineering. I'm decent with SQL, MATLAB, Python, various machine learning algorithms, and deep neural network frameworks like TensorFlow and Keras. I can work with support vector machines and random forests built with scikit-learn. I'm very familiar with the core Python libraries like Pandas and NumPy, which I'm sure we'll be using extensively here. And I also have a limited amount of experience working with weather data from a previous job. But I am not a meteorologist. I don't know the lingo. I'm not familiar with the best practices in the industry, or the field I should say, especially when it comes to hurricanes, which I imagine is going to be the focus of a lot of people's careers. What might take an existing subject matter expert here minutes to do could take me hours. And that's an important consideration. Machine learning is a very powerful tool, but to be truly effective with it, you also need to understand the subject matter that you're trying to apply it towards. Sure, you can learn as you go, like I'm doing to some degree here, but somebody who has a master's in a particular subject and then also learns machine learning is going to be far more effective at solving that problem. Okay, so with all that sorted out, let's form an initial preliminary problem statement that we can build on from here. Here's what I'm thinking. Government agencies need a system that can help them decide when to take action. Let's say it's 1% more accurate than the existing systems out there, and with more notice. Let's say 1 hour more than the existing systems, because the current systems are often incorrect X% of the time, or are not trusted enough to take meaningful action. It's not bad, but I'd like to get this nailed down a bit tighter, especially at the threshold levels that I have in there. I don't really know what the metrics for accuracy are in this field, and so I need to get a better understanding of what the current systems out there are doing and how they're measured, so I can set realistic goals. To do that, I need to do some research into the status quo and see if there are any other contenders I should look at as well. My search brings me first to NHC's website on NHC track and intensity models. But the list there is more than a little intimidating. Next, I find Weather Underground's site on hurricane forecasting computer models. This is much more digestible, plus they have a link to a recorded presentation that gives a nice historic overview and gives me a nice starting point. I learned that while it's old and not very good, the benchmark by which all other algorithms are measured is the old statistical Clipper model. From here, I find the National Hurricane Center forecast verification site, which contains some very useful data that I can potentially use to benchmark my system should I choose to build it in a similar way with similar outputs. But I notice on here that none of the models listed on any of these sites mention machine learning. They're either statistical or physics driven or some hybrid. From here I started looking into alternative approaches. And back when I initially researched this a few months ago, I found several interesting options here. So first, is this paper on predicting hurricane trajectories using a recurrent neural network. This one's interesting because it was done with just track data. And it was actually able to spit out some valid projections. It's a shockingly small amount of data to use, and yet it performed far better than I think I or anyone would expect. Instead of comparing it against the statistical baselines, they looked at the mandated target that's given to NHC. This could have come from some Senate or House Appropriations Committee, and it's not necessarily, grounded in reality. Still, the results are pretty compelling since the threshold is actually pretty low. And when you look at historic levels, this really shows us that machine learning clearly can work, even with such a simple approach.
And the chart that shows this threshold over time calls out the 48-hour projection for being, quote, often important for emergency managers and preparedness actions, which will be a nice piece of information to have when we get back to our objective.
Next, I found a project by a subsidiary of IBM that uses machine learning to predict damage to the utility grids. This is extremely relevant to the problem statement. However, I do have concerns about taking my project down this path. Having worked as a consultant to utility companies in the past, I know that the data this company used is probably publicly available, but I also know that it's usually pretty hard to find, unless you're familiar with the regulations and legal names of mandates in that particular state. And in this case, we have several states to consider, and I'm not really familiar with the regulations in any of those. So I think I'm apprehensive about going down this path. Maybe we'll come back to this later, but I don't want to get too focused on it just yet. The next approach I found was the deep learning based hurricane intensity estimator. This one was interesting in that they seem to use satellite imagery with each image centered on the storm to estimate just the intensity of the storms, not the track. The first approach focused exclusively on track prediction, so these two seem like they'd be pretty complementary, especially since the baseline models can output both.
The approach they take of centering the view on the hurricane is also interesting. Intuitively, I would think that using a global model would work better, since perhaps there's some major front just out of frame. But from watching the NOAA training video, it does seem as though this centering approach is used in certain physics-based models, so perhaps it can work. It's certainly something to keep in mind as we move forward.
Next, I found a paper about a project called Deep Weather that used modeled output from the ERA interim database at different pressure levels to forecast the weather. This was an interesting approach in that it combines machine learning with a physics model, but it doesn't depend on the physics modeled for the forecast, just for sort of an interpolation of statistics between weather stations. Next, I found this awesome article titled "Fuse Deep Learning for Hurricane Track Forecast from Reanalysis Data." This is a bit of a combination of several of the previous approaches. The fused network here involves essentially two neural networks that get concatenated together to provide a single output, or pair of outputs, latitude and longitude. The first half looks at the historic track data, just like the first approach did. The second network takes that same ERA interim data and combines it, in an interesting way. Runs it through a second neural network that then, links up with that track data neural network. Now, this approach also looks at a box centered on the storm, kind of like the hurricane estimator did with the satellite imagery. So it'd get me thinking about that approach a little bit more. I should point out that after I'd done this research, the author of this last project released another paper detailing the incremental next step that they took, which looks very interesting and actually might tie nicely with my second prototype, but we'll get into that in a future episode. Okay, so at this point, I felt like I had a decent sense for where I was going with this. The industry standard way of assessing the accuracy of these systems is to look at the average error, usually in nautical miles, but it could be kilometers, using great circle translation from latitude, longitude, coordinate pairs to distance, and then assesses the error over some time span. The best benchmark is to look at the most recent 5-year span, 2013 through 2017, through the end of 2017. Since, as NOAA points out, the average from one year to the next can vary quite a bit. And if this proves too limiting for our purposes, we should be able to instead select a random assortment of years spread over a longer time frame, as long as we compare our error for each of those years against the baseline error for the same time frame. They refer to this as assessing the error homogenously. Also, while the machine learning techniques being used perform well, they're only beating the NOAA benchmark, which is not the same as achieving state-of-the-art performance. While I have little doubt that a properly built machine learning approach can definitely achieve state-of-the-art given the correct set of inputs and the correct architecture, I think setting that as my objective here might be a bit ambitious given my time constraints. But it wouldn't be a moonshot without aiming for the moon, so let's try. We might fail on our first attempt, but there's nothing to say that we can't try again if our first prototype at least shows some promise. So let's get back to our problem statement. In my mind, there are two ways that we can, take this project. First, we could do something like what IBM's doing to predict damage to the grid, or similarly, something that predicts casualties, which might be useful to government agencies when trying to decide to take appropriate action. However, I see a number of problems with this approach, the biggest of which is that it doesn't take into account changes to building codes, local infrastructure, population levels, etc., since the last storm hit that area. True, we might be able to find some of that information, but I suspect it would take hundreds of hours to scrape together from local sources, and I just don't have the time for that. Plus, it's not something that we could easily benchmark. So I think the better route to take would be what people are currently doing, just with machine learning. I want to take this track forecasting approach and build a system that can do that with some new algorithms. There are far too few people working on this, in my opinion. And if we can inch things along even just a little here, I think this effort would have been worthwhile. So here's the problem statement as I see it. Government agencies need a hurricane prediction system with less average error in nautical miles at 48 hours in the future than the current state-of-the-art models provide, because they need to decide on actions to take to mitigate damage and save lives. And taking these actions can be costly, so they will only do so if they're reasonably sure they are necessary. Maybe that's a little verbose, but I think it really works. Now, from here we can decompose our objectives, state our original design requirements, and derive a couple more requirements that we should keep in mind as we progress through. The objective. The system's average error for 48-hour forecasted track locations should be lower than the best performing models evaluated by the NHC. Now note, I don't specify over what time frame this needs to be because I don't yet know how much data we'll be able to use. If we have sufficient training data, our test set should cover the past 5 years, but if for whatever reason, say we only have 7 years of data to work with, that would kind of be ridiculous. So we have to keep flexible here and keep open to a different approach.
Before I get into the requirements, here are a few quick notes. First, writing proper requirements is pretty involved, especially for larger systems. Most significant engineering design projects may involve writing hundreds of requirements, which can include performance requirements for each individual subsystem, interface requirements for how a user would interact with the overall system, how a system would interact with the environment, or how subsystems may interact with each other, among others. I'm not going to get into that level of detail here, and I'm going to keep the requirements for this system pretty high level, since the goal here is to build something pretty straightforward. The system I'm building is one of function over form, a proof of concept more than anything, due to my time constraints mostly, so I won't be spending any effort on building a nice user interface, for instance. With that said, there are a couple high-level rules to keep in mind even when writing high-level requirements for a simple system. First, requirements must be binary and clear. They are either met or they're not. If there are a requirement on some performance specification, like acceleration for a car, the requirement must specify a minimum threshold. Second, requirements must be traceable. In any system, there are a set of clear original requirements that come from the problem statement, and the high-level systems interface with the user and the environment. These are really what we'll be focusing on here, but in a more complex system, we would likely also be deriving requirements for each subsystem, as we may have an electrical engineering team working on one component and a team of software developers working on another. Each of their pieces of the project may have requirements that have to do with how these subsystems interact with other pieces of the original system, or requirements that relate to the original system requirements. Either way, there must be a clear, documented connection from the derived requirements to the original ones from which they came. Otherwise, over time, projects tend to become convoluted, with engineers thinking they have to do things a certain way because that's how the previous prototype worked. Poor project management can lead to untraceable requirements being given to these engineers for that reason, which can limit the options for a designer and thus limit performance and drive up cost. So with that said, here are the basic requirements for this system.
Requirements. The system must output at a minimum the latitude and longitude coordinates of the predicted location of the storm 48 hours from the timestamp of the associated input data. The system must store track data over the evaluation period for ensuring minimum performance specifications are met. Training time must be under 5 days on existing hardware. Data sources must fit within budget and be readily accessible. I'll not be filing applications such as Freedom of Information Act requests to get this data, nor will I go over budget or spend days looking through public filings to find it. That wraps up the problem definition step. I think we've got a solid start here. I hope you're getting as excited as me about where we can go with this. I think we're going to be able to do some really cool stuff with machine learning here. Next episode, we'll start exploring those possibilities. I hope to have that episode up shortly, though I'll be heading out of town in a few days, so it likely won't be until mid to maybe late next week. But make sure you hit the subscribe button so you don't miss it. See you next time. Moonshot out.